right, here we go on our the second video. So now we're asked to use rectangles to approximate the area under the parabola y equals to x squared from x is 0 to x is 1. So I have four pictures, four of the same images of the graph of x squared from 0 to 1. And so we're going to calculate the area in four different ways. This first picture, this first graph, we're going to calculate the area using left endpoint to determine the height of our rectangles. We're going to do, and we're going to use four. We're going to use four subintervals. So what we do is we take 0 between, what is the distance between 0 and 1? It's 1. And so we divide that by 4. So we're going to go over 0.25 on the x-axis and mark our, divide this up into subintervals. So if we go over about 0.25, that's about right there. This is another 0.25. This is another 0.25. So this would be at 0.25, 0.5, 0.75, and 1. Okay, so that is all. We've divided this up into four equivalent subintervals. And so we're letting the left endpoint where it hits the curve determine the height. So when we draw our picture this first time, right here at 0 is where it's hitting the curve. This right here is the height of our rectangle. The height is 0 for the first subinterval. Here's the second one. We're going to go to where it hits the curve on the left, which is right there, and draw, let that determine the height of our rectangle. At 0.5, go from the left side till it hits the curve. There we go. And then we're going to go across the width 0.25. There's our third rectangle. And then go to where it hits the curve on the left, and that determines the height, and we'll go across to 1. So this is the picture of our rectangles. While we're drawing this, let's go ahead and draw our pictures for this one, and then we'll do the calculations. Right here, we're going to estimate the area under this same curve, only we're going to do R sub 4. What that means is we're still going to use four subintervals. So we'll take 1 and divide it by 4, and we get 1/4, or 0.25, and we're going to go over here, and we're going to mark up our x-axis in divided into 4. So go over 0.25, and then go over another 0.25, and then go over another 0.25, and then 1. Okay, so this is 0.25, 0.5, 0.75. Only this time we're going to go from the right endpoint. So that means if this is my rectangle, I'm going to go to where it hits the curve on the right, and I'm going to go across 0.25, and this is going to be my first rectangle. And then at 0.75, I'm going to go to where it hits the curve, and I'll go across at 0.5 from the right, at 0.25 from the right, and across. So we can just see from these images the way this curve is drawn. The left endpoints are going to give us an underestimate of the actual area. And the right endpoints in this case give us an overestimate of the actual area. But it's something. So here we go. Let us go ahead and do the calculation. So what we're going to do is we're going to add up the area of each of these rectangles. The first one right here, this one, it has a width. The area of a rectangle, let's just recall, is equal to length times width, right? Or, length times width. So I'm going to let my width right here is the same for all of these. It's 0.25. And the length is going to be the height. So for this first rectangle, his area right here is 0.25 times the height, which is 0 in this case, because we went from the left endpoint. Right here, or in fact, let me do it this way, f of 0. So 0.25 times f of 0 plus 0.25 times f of the left endpoint this determined the height, f of 0.25, plus the width, 0.25, times the height was determined by this point on the curve, f of 0.5, plus 0.25 times the height, which was determined from the left, f of 0.75. So I wrote down this, I did a little point plotting, or I did a little table for us so you guys could just plug in the values right here. It'd be real easy. What this is to calculate this will be 0.25 times f of 0, which is 0, because our curve is x squared, plus 0.25 times f of 0.25, which is 0.0625, 0.0625, plus 0.25 times f of 0.5, which is 0.25, plus 0.25 times f of 0.75, which is 0.5625, 0.5625. You can add all this up, and you find that the lower estimate, L sub 4, is 0.21875. All right, that's what we got. That's what the area of these rectangles add up to be. On the right side, what we would do to add these up, the width is still 0.25, so it's going to be 0.25. This first rectangle times f of, we let the right endpoint determine the height, so it's going to be f of 0.25, plus the width, 0.25, times f of 0.5, plus 0.25 times f of, we let 0.75, plus 0.25 times f of 1. And you can use these values and plug these in, and you will find that r sub 4 is equal to 0.46875. All right, now, the true area lies somewhere between L4 and R4, because this was an underestimate and this was an overestimate, so the real area is going to be somewhere between those two. All right, what if we do this one more time and we do it with 5 rectangles instead of 4? We increase the number of rectangles by 1. L5, let's see. So 1 divided by 5 is 0.2, so now we're just going to go over 0.2 and mark this up. So this is, we're going to have 5 rectangles, so this is going to be 0.2, 0.4, 0.6, 0.8, 1. And if we let the left endpoint determine the height, this height will still be 0. And this height will be here, this height will be here, this height will be here, and this height will be here. And we are still getting an underestimate when we do this. Let's see. The width is 0.2, so I'm just going to factor out the width. And so it's going to be times the height, f of 0, plus f of 0.2, plus f of 0.4, plus f of 0.6, plus f of 0.8. And so, let's see, that's the height, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That's the area of our 5 rectangles right there. And so if you add that up, I provided the values right here, the table values, that you can just plug these in. And so you guys can calculate this. This would be 0.2 times 0 plus 0.04 plus 0.16 plus 0.36 plus 0.64, and you find that L sub 5 is equal to 0.24. L sub 5. Okay, so we could do, I'm going to go through drawing this one more time so you guys get really good at drawing this. This is going to be R5. We're going to do this. We're going to split this into 5 subintervals, 5 rectangles. And so you take 1 minus 0, which is 1, and you divide it by 5, and you get 0.2. That tells you the width of each of your rectangles. So it's still going to be 0.2, 0.4, 0.6, 0.8, only this time we are going to let the right endpoint determine the height. So you go over here to the right side, and that's going to be the height of the first rectangle. To the right, this is going to be this, the height, 6. This will be the height of this rectangle. This will be the height of that guy. And this, the right side hits right here, and that will be the height of this one. And so you can see we will get an overestimate. And so the width is 0.2. It's going to be 0.2 times f of 0.2. 0.2, the width, f of 0.4. 0.2, f of 0.6. 0.2, f of 0.8. 0.2, f of 1. And this is what r sub 5, we add up the area of these 5 rectangles, and you find that r sub 5, you can plug in these values, is equal to, what did I get? 0.44. So let's just see, let's just take note of some things. Okay. L sub 5 is 0.24. It is less than 0.44 because, of course, this is an underestimate and this is an overestimate. So what we know is that the true area is going to lie between L5 and R5. Okay, the true area. But if you take note, 0.24 is a little bit bigger than 0.21, what we got with 4. And 0.44 from the right side is a little bit less than we got with 0.46. So what we're finding is that when you increase the number of rectangles, you get a better estimate. You get a little bit closer to what the real area is, what the true area is. And so that is a big deal. It's kind of the method of exhaustion. If you remember on the first sheet, as they increased the number of sides of the polygon, it got closer, you get a closer fit to the area. So the lower sums is where you choose your x value. In general, a lower sum, let me draw a little picture and this will illustrate it. Here is, if you had some curve here, let's just say we had some curve. Okay, and we wanted to know the area between this A and B. All right, so we split this into subintervals. We could, here's just, okay, we'll do between here and here. So we'll say this is our endpoint here, A, that we're interested in the curve between here and here. So let me just erase this off because we're not interested in this part. Okay, between A and B. Now, the lower sums is where you let your height be the lowest point of the entire place on that. So I'm going to do the lower sums in blue. In this particular rectangle, this is the lowest point. That would be the lowest sum. In the second one, this is the lowest sum. In the third one, this is the lowest place that I have. In the fourth one, this is the lowest place. So if I added up this is called the lower sums right there. When you let the height or your x value, let the height be the lowest. And so what they call this is where you let your x value, x sub I, be at the lowest place on the sub interval. Okay, so I could draw these rectangles, and this time I'm going to draw it with the upper limit, the upper sum. That's where when you look at your subinterval, you pick the highest place. So for this first one, this would be the highest place. That would be the upper sum. The second one, this is the highest place. This would be my upper sum. The third one, this is the highest place. This is what the upper sum would be. And on the fourth one, this would be the upper sum. So the upper sum is the same thing, except for you let x sub I be at the highest point on the sub interval. So here's the big deal. it can be shown that area is the unique number that is bigger than all of the lower sums and smaller than all of the upper sums. So, and they didn't say if you take 4 subintervals or if you take 5 subintervals. There's no limit. So if you took like 80 rectangles, if you split it up into 80, still the area is going to be the unique number that is between the lower and the upper. So if you took more and more rectangles, that is going to get more fine-tuned and more fine-tuned. So finally we get a definition of area, and here it is. All right. The area A of the region S that lies under the graph of the continuous function f is the limit of the sum of the areas of the approximating rectangles. So this is what we were just doing. We were saying width times height, width times height, width times height. So if we added up a bunch of the areas of rectangles and we took more and more rectangles, so what this says is the area is equal to the limit, as in the number of rectangles that you take goes to infinity. So this happens to be r sub n from the right side. This is one definition of the area. So the limit, as you let the number of rectangles increase to infinity, is equal to the sum of all these little rectangles. But there's another definition like this, and they've changed this r sub n to l sub n. And because it doesn't matter if you take more and more and more rectangles and you let that number of rectangles approach infinity, then it does not matter if you take the height from the left side or from the right side or from the midpoint, or in fact anywhere you wanted to choose it on the subinterval. It doesn't matter because you're taking so many rectangles at that point. It's going to be it's going to approximate the area exactly. So for that reason, and later you'll see other definitions where they have this not x sub 1, but they'll call it, you'll see it, it'll say x sub I star, and this means you can take it from anywhere on the subinterval. Take the height anywhere. So here's the big idea. Here's the big idea. It says, the more the rectangles are used, the more rectangles are used, the better the estimate. And if you take the number of rectangles close to infinity, then it's going to be an exact estimate of the area. Okay, I'm going to pause and we're going to do the last one together in just the last video.